so let us continue from where we left in the previous video. So, in the previous video you were actually analyzing, you were actually going through step by step process for the analysis of buffer delta network. So, I had discussed about the Petri-net model I think in the previous video, and then of course, we also talked about T select is equal to 0 or T pass is equal to 0. So, one of the two things, and then how we are going to do the modeling with that. I had also explained that what is the consequence of when T pass is 0 or when T select is 0. So, if we look at a cascade of a switch, I am just repeating that. If we look at the cascade of a switch, there are two packets at the input. This has to go to another switch and so on. So, I am only taking 3 stage system. So, when T pass is 0, that actually means that packet transfer happens almost instantaneously, while selecting a packet takes one full slot. Okay. So, what will happen is the situation of what will happen to the buffers is being propagated almost instantaneously, that is what I am assuming, and then the selection can be done at all the stages simultaneously, and then packets can be transferred almost in 0 time. So, in the first time slot, these two packets which are contending. So, once the time slot is going to be over, that time we know which packet has to be transferred, and it will be transferred almost instantaneously. So, at the beginning of the slot, next slot, you will have a situation that this packet is already moved here because this has won the contention. Now, again in the next full slot, in this particular duration, they will be now doing the decision process and the selection will be happening, and at the end of this almost instantaneously this packet will move here and this packet can also be moved here. Okay. So, you will have a situation where this packet, we will have a situation when the packet here will move here and there is another packet on this side, and at the end again in the next slot the selection process will happen, and then almost instantaneously the packets will be transferred. So, one will go on the outgoing port and then this will be immediately removed. Okay. That is what will happen with T pass is equal to 0. Instead, if the T select is equal to 0, we are going to take. So, in that case, when initially the two packets will be there, and it will not take much time to select which one of them has to go to that, but only one packet can be going and it will take one full slot period. Okay. So, instantaneously decision is made which one will go out. By the time you reach here, this packet would have been completely transferred at this position. Okay. Now, at this position, unless this slot is empty, you cannot write this packet here, because in the earlier case when T pass was 0, this packet was instantaneously emptied and next packet could have been pushed in. So, all packets actually do the jump and there is a cascade effect which cannot happen here in this case. So, it will take one full slot for the packet to transmit here. By the end of this is the situation. In the next time slot again decisions will be made, but this slot is not free. This will take one full slot to get emptied and this packet will reach here at the end of this slot, but this has to be hold up because you do not have the buffer empty here. Okay. This buffer get emptied only at this position. So, now at this position again these packets will move and I will have a situation where the packet, one packet is here and one packet is here, and it will take one full slot to read out onto the outgoing line. So, that is the difference between T pass is equal to 0 and T select is equal to 0. Now, of course, everything is going to happen in now 3 steps when T pass is 0. So, let me see what are those steps. So, we will be first of all analyzing T pass is equal to 0 case. So, this is the case which we are analyzing. So, step 1 will be when the packet moves out from the output to free it. Okay. So, if I am talking about a switch, it might be having a packet on the outgoing buffer, so this has to go out first. So, within one slot I am actually defining these 3 steps which are happening, and this is basically a kind of an assumption which we have made. This will simplify my computational process. After step 1, the step 2 will be happening. Step 2 will be happening where the packet will move from input to output. Okay. And then there will be a step 3 where packet will move from the previous switch to the input actually. So, packet will move to free input of the switch. So, these 3 things, these are the fictitious steps which we are going to have, and at stage n minus 2, in fact if you look at the last stage will be n minus 1. So, stage n minus 2 will be connected to that. Now, remember the case which we are considering, the t passes 0. Okay. So, when t passes 0, so the packet will be instantaneously removed out. So, which actually implies that any packet which is here will always be removed, because there will not be any packet here. This will be always become free, these outputs. So, any packet at this point will always be moved out. So, they will always be emptied actually. And state probabilities. So, every switch I will identify as what are the possible states in this case, and this state probabilities, these states can do a transition from one state to another state. So, we will find out the state probabilities after step 1. Okay. We will find out the state probability after step 2, state probability after step 3. This will become the probability which will be used here in the next time slot. So, this is one full time slot actually. So, the state probability after step 3 will become the initial state probability before step 1 in the next time slot. So, we can now formally define what will be these state probabilities. So, let me define these, and then we will actually consider the transition probabilities we will estimate. So, P of 0, this is basically in the current time step, what is the probability of being in state here. This is basically after step 3 of the previous time step. Okay. So, P0 1 j actually implies here. So, this is in time step tau k. Okay. So, this k signifies this particular time step, and I define this as I. I means it is the state I, j means the stage j, the switch is in stage j. All switches in stage j will have the same probability distribution. So, this we have already done as one of the lemmas, and 0 means this is a step 0, which is basically after the step 3 of the previous time step. Okay. So, this will be written as probability that switch in stage j is in state I at time is equal to Tk. So, remember tau k step. So, when I draw a timeline, the Tk is this time instant, and this particular time interval is tau k. Okay. So, Tk is that particular time step. So, we will also define, once the first step has taken place, then the state probabilities will be different. So, this is the probability that after step 1 you are in state I in stage j in this time interval tau k. So, this will be written as probability that switch in stage j is in state I after step 1 in interval tau k. Okay. So, similarly we can go for the next one, this is after step 2. So, I can write this as probability of switch in stage j is in state I after step 2 in interval tau k. So, we can define further P3. So, let me write down the P3 on this side. So, this will be probability of switch in stage j is in state I after step 3 in interval tau k. Now, interestingly, this P3ij should be equal to P0 ij in k plus 1. So, this is important, this is what I had emphasized earlier. We also now define certain other probabilities. So, we can define Pj tilde. So, this will be probability that a packet at switch output link in stage j is passed out, basically move to the next stage buffer in interval tau k. So, we can actually now we need to figure out what are the states before we actually start estimating this Pj tilde, and there is another probability we will define Pj bar, and based on that we will make the complete estimate. So, ultimately what we want is we want to find out what is going to be the throughput, which will be Pn minus 1 tilde, the probability that packet will be going out of a this of course is a conditional probability. So, we have to find out what is going to be the throughput using this particular procedure. So in fact, if we look at, as I defined, that in the n minus second stage, if there is a packet, it will certainly go out. This is a conditional probability. If a packet is present, it will be going out, conditioned on that. So boundary condition for this one will be that Pn minus 2 tilde will be 1.0. Okay. And then of course we also define, if there is a Pj that packet will go out, there is also a probability packet will not go out. This has to be complementary of this. So I will define Qj tilde will be equal to 1 minus Pj tilde. So this is the boundary condition which we can actually use. So we need to look into now the states. So let me list down all the states which are there. So I can write down the states. So we will essentially derive all possible states which can exist in a 2 by 2 switch. So switch is like this. It has 2 outgoing ports and 2 incoming ports, and packets can be stored at input as well as output buffers. Okay. So basically the output buffers are nothing, they are the input buffers of the next stage switches. So first possible state is when there is no packet being buffered, I call this state as 1. Okay. So next possibility, I will now look into one packet being put on the outgoing side. So if this is buffer, there is no packet on the input side, this we call the state 2 of a switch. Third possibility is that we will have 2 packets on the outgoing side. So this is the third state, there is no packet at the input. Now I have exhausted all the possibilities for the no inputs at the input buffers, no packets at the input buffers. I am only consider the output side. Now let us consider one packet at the input buffer. So if I have one packet at the input buffer, there is no packet at the output buffer is one possibility. I have to also give a direction. So this packet can go here, this is actually state is equivalent to this state, these two are same states actually. So I can always swap these two outputs, okay. I can always twist them around and this will turn out to be the same thing. So there will be only this state which is possible. So I define this as state 4. Then it is possible to have still one input and I can have one output. So the packet can be directed to this particular thing. So or there is a possibility that packet can be directed to free outgoing port. Now all other combinations, for example, I can always say a switch might have a situation like this, there is a packet here, there is a packet here, there is a packet here and this is going here. Now these two are actually same conditions. So this essentially merges into this particular state, okay. So there is a possibility of similarly for example having a switch here and doing it, this is also the same, okay. This is the other one. So we can have similarly all possible combinations you take. So this is nothing but the same condition which is there on the other side, the sixth one. So this is the fifth state and this I define as a sixth one. So if I can by twisting the inputs around there, if I can map onto something, then that is being merged in that states. So this is the fifth one. Then I can define fourth, this is the fifth and this is the sixth state. I can now define the state with one single input and two outputs. So this is going to be directed here. So if it is not directed here, it is directed here, this actually means the same thing, okay. So there is only one possibility here, we define this as state 7. Now I have to start with two inputs being occupied. When there is no output and two inputs, there are two possibilities, okay. Both of them are being directed to the same output. So, if both of them are directed here or here, it is the same thing, it will essentially degenerates into the same state. So, I call this state 8, and then we will have two free things and they are being parallelly going out. This is state 9. Okay. Then of course, I can have situation when there is one input, two inputs and one output. So, both of them can be directed to the port where already the packet is there. I call this state as 10. It is possible that both of them get directed to the bottom side. So, in this case, so one of them going to this occupied one, other one into this. In fact, this state is same as if I draw it the other way around also, this is same actually. So, both of them are same. So, I am going to just use this. This we call state number 11, and then of course, when both the inputs are being directed or are being contending for the free output port, this is a state number 12. Okay. Now, I have actually exhausted all ones with two inputs and one output, and now I have to put with two outputs and two inputs, and there are only two possibilities. So, one is these two are trying to go to the same outgoing port, this is a state number 13, and then we have this as a state number 14. So, even whether even this being crossed, so the top input is trying to go to the bottom output, bottom one trying to go to top one, is same as the state which is already shown. There are only 14 possible states which are distinct. All other possible states which can be there for a 2 by 2 switch can actually be represented by these itself equivalently. So, these are the non-equivalent states which are possible. So, we can now write down in terms of these my Pj tilde. Okay. So, let me explain how we get that. Pj tilde will be essentially, this is a packet, this is a conditional probability that a packet is there in the outgoing port, and in the next time step after step 1, or this packet is being moved out, that will be happening after step 1, because in jth stage the packet actually goes out of the outgoing port only after step 1. Okay. So, this Pj tilde will lead to transition. After step 1, the states will change for the jth stage switches. Okay. So, this will be essentially responsible for that. So, I need to find out the probability first of all, because it is a conditional probability that a packet is there in the output buffer. Okay. And then of course, we will have, so this should be after step that a packet is there in the output buffer of switch in stage J. This equivalently implies the input buffer of switch in stage J plus 1. Okay. So, these two are equivalent actually. And this is the probability that in step 1 sorry, I will rewrite it in slightly different way so that it can be clearly communicated. So, what is happening is in stage J, this is connected to stage j plus 1. Okay. So, j plus 1 already the packet has moved out, that is a step 1 which has happened. So, now the what is happening is after the step 1, when step 1 is already over. So, step 2 is this packet will be transitioning from input to output actually. So, I am trying to estimate what are the states after step 1 where there is a packet which is present here. Okay. So, that I will be using numerator, that is a probability that the packet will be present there, and then I will find out that after step 1 what is the probability that this switch is in the state, in such states where a packet actually can transition in the step 2 of this one, which corresponds to the step 1 for stage j. So, remember when the step 2 is happening here, step 1 will be happening here, okay. And then of course, step 3 will be happening in the next one, because the packet will be arriving there in their input buffer. So, I need to find out in j plus first stage what are the state probabilities where you will actually have a packet at the input of j plus first stage switch, which also implies the output buffer of the stage j switch. So, I should write it as probability of being in state after step 1 in j plus first stage switch such that there is a packet in the input buffer of switch in stage j plus 1, okay. And of course, this probability will be of being in a state after step 1 in switch in j plus first stage such that packet can move to output of the switch in step 2, okay. So, let us look into, we actually have to maintain these states, and based on that we will decide, we will actually write down the expression for this. So, this expression I have to write down all the numerator and denominator terms. So, for Pj tilde I have to find out the states. Now, remember I am talking about the j plus first stage switch and step 1 is already over, okay. So, do I have a packet at the input after step 1 in j plus first? So, you cannot be in this state, there is no packet at the input, there is no packet at the input, there is no packet at the input. If by chance the switch is in the fourth state in j plus first stage switch, then there is a packet, but with half probability the output which you are considering can be this one, and with the remaining half it can be here. So, I need to write down that it will be 1 by 2 P1, this is after step, you are going to be in state 4, stage j plus 1 in time step k, okay. So, with that probability you will have a packet at your at the output buffer of the switch in jth stage. Okay. Now let us look at the next one. This one also contains only one packet, so with half probability this also I need to put in. So I will put half p of 1 5 j plus 1 k. We can keep on looking, so similarly I need to do it for 6. So wherever there is only one input port having the packet, I will do that p1 6 j plus 1 k, 7 also in the same fashion, 8 actually both the inputs have the packets. So with equal probability you can have this or this connected to you. So which actually means this time there is no half, I have to have 1. So I will be putting p1 8 j plus 1 k. So p9 similarly p1 9 j plus 1 k, p10 you can be in p11, p12 and p13 and p14, so all of them will come. Okay. So this is what will be the denominator, this is this probability. Now I have to look at the cases where packet actually will be transferred when the step 2 is going to happen in j plus first stage switch. So 1 there is no movement, so 1 cannot come in the numerator. 2 again there is nothing is going to happen, so packet cannot move, there is no packet at the input of the j plus first stage switch. 3 again the same case. In 4th, yes, the packet will actually be going, but this will be only happening with half of the probability. So half p1 4 j plus 1 k. So next in the 5th there is no possibility because there is a blocking, so output buffer is not empty. In 6th it will be happening, but that will be again with the half probability. So you have to note this, I am actually talking about jth stage, so I am using j plus first stage state probabilities. And similarly look at 7, nothing will happen. In 8 though you actually there are 2 packets at the input, but only one of the packet will be going out. Okay. So with only half it will be happening, so we will be putting half p1 because you might be actually talking about a packet which is this one, it cannot go through, with only 50% probability it can go through. So p1 8 j plus 1 k. Then similarly when you look at the 9, both of them will go out, so I have to put full. In 10 they cannot move out, so it will not be coming in. 11 only one of them actually will go. 12 only one of them will be going. And of course 13 and 14 no packet can go to the outgoing port. So this is what will be your expression for pj tilde. Okay. And boundary condition for this, as I mentioned, will be I need to write it here itself, Pn minus 2 will be always 1.0, okay, that happens, and of course Qj tilde will be equal to 1 minus Pj tilde. Okay. So these are the conditions. We also need to define something called Pj bar. Okay. So let us define Pj bar. Okay, I need to still maintain those state tables, so I have to write on this side of the board itself. So I will just make a change. This is the probability. I will just redefine it. It's Pj bar. So probability of being in state after step 1 in j minus 1 stage, this is the probability of arrival. Okay. So this is a probability that a packet from an input link at j minus 1 is placed in a buffer at the output link. So in the previous stage the packet is going, the step 1 is happening in the previous stage, in your stage step 2 is happening. Okay. So I am talking about j minus 1, and in terms after step 1 in j minus 1 you are actually going through step 2 now. Okay. So probability of being in state after step 1, so their step 1 is already executed and your step 2 is already finished, that is what it means. So after step 1 j minus 1 state switch such that input buffer such that the input buffer of switch in stage j is free. Now this input buffer in stage j is free actually technically also equals output buffer in switch in stage j minus 1. Okay. So this we will again decompute. This boundary condition will also. So denominator I have corrected. So for Pj bar, probability of being in state after step 1 in switch in j minus 1 here stage such that the packet can move to the output of this switch in step 2. Okay. So we have already finished step 2. In j minus first stage step 1 is finished and this is what is going to happen. So when step 2 is going to be executed in j minus 1 first stage, the packet has to move to the input buffer. So we are now looking into conditional probability of arrival. So conditioned on that the input buffer of jth stage switch is empty. So let us look how we will find out. So I need to look into these states. I am looking into j minus first. So the switch is something like this. So this is your switch. Okay. So you have to find out whether this is free or not free, and then the packet will be moving. So this step 2 will be executing here for the movement. So after step 1 which has happened here, there should not be any packet here, that is the first thing. And if there is no packet, what are the chances that packet will come? So you have to find out what is the state of this switch after step 1. So that will be governing. So let me actually list down in the denominator all the states such that this input of this particular switch or the output of this switch j minus first stage switch is actually free. So let us look at those and then write down the expressions. So if j minus first, remember I am looking at j minus first stage switch, outputs have to be free. So when you look at the state 1, both the outputs are free. So with equal probability both or any one of them can be connected to my switch in stage j. So I can write down here P1, you have to be in state 1, j minus 1, okay, after in time step k. So this will go in the denominator. Look at the state 2, with half probability I may have a packet, and with another half I will not be having the packet. So, I will put half here, half P1 K U is the state 2 in J minus first state switch. Then similarly I will have the third one there is no output buffer which will be empty, or the input buffer for my switch in jth stage, because I am talking about that, and sorry, this is Pj bar. So, third one will not come, the fourth one, yeah, both of them will come. So, this will be half P of 1 4 J minus 1 K. Then we will have the fifth, there is with half only this will be happening. And then we will have sixth with half only it will be happening. The seventh cannot be there because output buffers are not free. Eighth both are free, so is without half. Ninth both are free, so it is again without half. And then we look at 10th, only one of the port is free, so 10th, 11th and 12th will be with half actually. Tenth, 11th and 12th. So, this completes my denominator. Okay. So, then the numerator part is I have to look all those states where the actually packet will be coming in. So, when you look at the state 1, there is no packet which will be coming in the next step. So, there is no arrival which is going to happen. So, this will not be listed in the top. So, conditioned on when the input buffer is free, I will not be having any arrival. When consider 2, nothing will be arriving. Consider 3, nothing will be arriving. In fourth, yes, the packet will be arriving with half probability. Okay. So, I will write half P1 4 J minus 1 K. Then you look at fifth, no packet will be arriving. You have to look at the arrow direction also. In sixth, yes, packet will be arriving with half probability. Okay. So, I will write plus half P1 5 J minus 1 K. Look at now the sixth one. Sorry, this one was should be sixth, not fifth actually. The seventh, nothing will be happening. Eighth, only one of them will be coming, so I will put half. Ninth, both the packets will be arriving, so I will write P9, there is no half here now. The 10th, there is no arrival. 11th, there is only one which will be arriving, so I will put half. And 12th, only one will be coming, so I will put half. (13) and 14 will not be there. So, this what actually completes the expression for Pj bar. Now, boundary condition for this will be that P0 bar will always be equal to 1.0. This is a complete maximum loading condition which we are looking into, and then of course, Qj bar will be equal to 1 minus Pj bar. So, these are the two boundary conditions which will be there. So, arrival probabilities will be now being controlled from the input side, because input P0 bar is fixed. Similarly, for the departure probabilities Pj tilde, the Pn minus 2 tilde will be equal to 1.0. Okay. So, now once we have these, we can build up the state transition table. So, for the jth one, so I will still keep that state diagram here, and show you how you build up a state transition table. So, remember with the state probabilities I have built up the transition, I will now generate transition probabilities Pj bar using Pj bar and Pj tilde, which are function of the state probability. So, we will do actually iterative computation essentially. So, for the state transition after step 1, so we will have states going from 1, 2, 3, 4, 5, 6, okay. So, if you are in state 1, what will be your next state after step 1, okay. So, look into state 1. After step 1 there is no departure thing here, okay. So, step 1 is when the packet will be departing. So, you will still remain in state 1 if you are currently in state 1. So, with probability 1 you will remain in state 1. So, rest all elements will become 0. I am only putting the non-zero elements here. If you are in state 2, now this can go out with probability Pj tilde, and with Qj tilde this may not go out. So, with probability Pj tilde you will come back to the state 1. So, I can write Pj tilde, and with probability Qj tilde you will remain in state 2. So, now interestingly, because by using j minus j plus first state probabilities you can compute the transition probabilities for the state j, and then if you know the current state probabilities you can actually estimate that the new probabilities using this algorithm. So, the third one, if you are in state 3, so you can remain in state 3 if none of the packets goes out. So, you will remain in state 3 with Qj tilde square. If only one packet goes out, other one does not go out, which will happen with 2 Pj tilde Qj tilde, you will come to state 2. So, I can write here 2 Pj tilde Qj tilde, and of course, if both packets goes out you will come to state 1, okay. So, we can keep on doing it. So, let me just put in all the valid entries which are there for this. So, once you know the procedure you can actually compute.